Hi everyone, this is Statistics Chapter 4, specifically 4.5, Counting Techniques. So what we're looking at is the classical method when all outcomes are equally likely involves the counting of numbers of ways that things can occur. So in this section, we will include techniques for counting the number of results in a series of choices, and I have that highlighted, under several different scenarios. One of the techniques we're going to use is what's called the multiplication rule. What the multiplication rule is, if a task consists of a sequence of choices with P selections for the first choice, Q selections for the second choice, and then R selections for the third choice, and so on, then the number of different tasks is P, the first choice, times, hence multiplication, the second choice, times R, the third choice, and so on and so forth if you have more selections. And again, this is a sequence of choices. So it says in the first example, a child is coloring a picture of shirt and pants. Okay, well, that's important, shirt and pants. If there are 5 different colors of markers, then how many ways can the shirts and pants be colored? Okay, well, kind of the classical way of doing this is the way I'm going to present it now. Is we have shirts and we have pants. Well, looking at this is that there's 5 different colors of markers to color or paint a picture of shirts and pants. So of those colors available, I can choose 5 colors for the shirts, but I can also choose those same 5 colors for the pants. When you do that, then how many ways can it be colored is 25 ways. And looking at this too, something that should be noted is, say for the shirts I used blue, well then for the pants I can use blue as well, meaning that that color can be repetitive. It can be used again and again. So in this example, it should be noted that repetition is okay to use. It's allowed. Let's look at the next example. Let's say the child is coloring a picture of a shirt and pants again, but now the child wants to use 2 different colors. Use 2 different colors out of the 5. How many ways can this be colored? So again, we can't use the same color twice like we did in the first example. We can only use different colors. So we're going to have the same setup here where it's going to be shirts times pants. But this time it's going to be a little bit different because our shirt or shirts, I can use 5 colors or have the possibility of utilizing 5 colors, whereas my pants, I can't use the same color that I used on the shirt, so I only have 4 possibilities from there. And I'll show you a different way of seeing this. Say we used blue, green, red, orange, and yellow. Just say for the shirts I used blue. Well, now there's only 4 possibilities for the pants, hence why I have 4. Thus, because we see this, repetition is not allowed in this. And the key giveaway was it said 2 different colors. So again, I'm going to say that it is very important. Repetition is not allowed. So 4 times 5 is 20. 4 times 5 is 20. Okay, now we're moving on to something a little bit new. I mean, the other one was new as well, but what we're looking at is factorials. So if n is greater than or equal to 0 and it's an integer, the factorial symbol, which I don't know if, let's see if I can highlight that a little bit there. There you go. It's like the exclamation mark, like somebody yelling, basically. I don't know if that would be exclamation, but is the factorial symbol n factorial. And how that is defined as follows. We'll have n factorial equals n times n minus 1 times n minus 2, and so on and so forth. And there's kind of some special examples down here. 0 factorial equals 1, and then 1 factorial equals 1. And you'll want to know those. So now that we call this kind of in a word sentence, let's go ahead and kind of zoom in on it, and we'll show you an example of what all this is talking about. So right here it says calculate 5 factorial. I'm going to utilize the example above to kind of explain what that formula means, and then I'm going to do it in a very simple way. So my n represents 5 times 5 minus 1. Well, 5 minus 1 would just be 4, right? Times 5 minus 2, well, that would just be 3. And then I would do 5 minus 3, well, that would just be 2. 5 minus 4, that would be 1. And then, right, you would end at 0. Well, that's what 5 factorial represents. What this represents is 5 times 4 times 3 times 2 times 1. That's what everything I just did represents. Let's make it small. Now, what this says, again, is 5 factorial. There is a way to do this in the calculator. So you want to pull out your calculator, and I'm dealing with 5 factorial. So let's put in 5 in our graphing calculator. Then what you want to do is on the left-hand side, you're going to see the word math on your calculator. Go ahead and hit that, and it's going to bring a screen. Your screen might look different than mine. My graphing calculator on my iPad is limited to what I can choose. Up at the top, you'll have the different selections. You want to go to the selection that's PRB for probability. And we're going to utilize all of these in this section, but just for right now, we're going to utilize the factorial sign, number 4. You're going to hit that and hit enter. Now your screen should say 5 factorial. That's what it wants us to calculate. Go ahead and hit enter again, and you should get 120. 120. Even if in your calculator, even if you did 5 times 4 times 3 times 2 times 1, let me clear that. That did my answer. 5 times 4 times 3 times 2 times 1, you should get 120. So you're kind of seeing, again, the connection that's being made there. Putting 5 factorial in your calculator quickly and easily makes things a lot easier. All right, next example. If I need to run errands to 6 different places, then how many different routes are possible? Well, you have a lot of routes here. So this would be, say, Route 1, Route 2, Route 3, Route 4, Route 5, and Route 6. So there's 6 different places. I'll highlight that for you. How many different routes are possible? Well, you're running errands, and let's just say you're going to the grocery store or something. So you're driving from your house, and there's 6 different grocery stores. You have an option to choose any of them. We'll say you just choose one of them. You go shopping there, they didn't have everything you need. Well, if they don't have something that you need, well, then you need to go to the 5 other grocery stores or shopping stores that are available to find that item that you need. Well, there's only 5 other options left. Well, let's say you go to that option, and you got a little bit more of what you need, but you still haven't got everything. Well, you wouldn't go to the one that you first went to. You wouldn't go to the one that you're at now because they didn't have the other things that you need. So then you only have now 4 stores or 4 options left. So you'd have 6 times 5 times 4 times 3 times 2 times 1. This should look very similar to the factorial idea that we just did in the one above. Or you could write this as 6 factorial. Let's do a little practice with our calculator again. Let's put in 6 in our calculator. We're going to go to the word math. It brings us to a menu of options up at the top. We're going to go to PRB for probability. Hit the factorial sign, hit enter. It will say 6 factorial in your main screen there. Hit enter again, and you'll get 720 for your solution. And in other words, if you did 6 times 5 times 4 times 3 times 2 times 1, you would get 720 again. So it's kind of a quick and easy way of getting the solution rather than typing out a bunch of numbers. I mean, again, this could be 10,000 factorial, and you wouldn't want to do 10,000 times 9,999 times 9,998 times 9,997 and go all the way to 1. That'd be crazy. So it's a quick and dirty way of kind of getting to your solution very quickly. Now we're looking at another example. A lock combination requires 3 distinct digits and 5 distinct alphabetic letters. How many different lock combinations are there? Okay, just to kind of give a quick example of what a digit is. that's just numbers 0 through 9. So you'd have 10 possible digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible digits. Very similar to the sample space that we saw in prior sections. And then there's 5 distinct alphabetic letters. Let me highlight that, and then this is important. We're going to assume, well, we'll just keep that there's 26 alphabetic letters. I know there's capital case, lowercase, things of that nature. Just keep it at 26 to make things simple. And it's asking us again, how many different lock combinations are there? Well, it's saying that we're using three distinct digits. So let's do 1, 2, 3. And this here is going to represent our digits times 5 alphabetic letters times 1, 2, 3, 4, 5. And this here is our letters. All right, well, how many digits are possible to begin with? 10 possible digits, and then you have 9 digits, and then you have 8. So that's the combination for the 10. Well, now I need to deal with alphabetic letters, and there's 5 distinct ones. Well, to start off with, you have 26 letters. Then you have 25, 24, 23, and then 22. Well, when you do that, when you put that all in your calculator, I'm going to need a little bit more space here. Let me shrink that down. Hopefully you could see it. What you would get here is, what is that? 5,683,392,000. So you would just do 10 times 9 times 8 times 26 times 25 times 24 times 23 times 22. And that's how many different lock combinations there are. So quite a few. And if you notice, a key example here from what we learned prior in this section is that repetition is not allowed, meaning you're not utilizing the same digit over and over again. If you were, you would have a different set of combinations, and thus you would have a different solution size or combination size. Next example here is at a film festival, the director must select a film from each category. There are 8, I'm going to highlight this, 8 drama films, 3 sci-fi films, and then 5 comedy films. How many different ways can be selected? All right, well, we have drama times, we'll have sci-fi times comedy. Well, how many drama films are there? There's 8 drama films. How many sci-fi films are there? There's 3. And then how many comedy films are there? There's 5. There's 5 comedy films. So when you put that and you get your solution from your calculator, you would get 120 ways a film can be selected. So quite a few. Let's go ahead and box that one above it. All right, now we're going to move into solving counting problems using permutations. So there's kind of some rules and things we're going to look at for permutations, but the definition is a permutation, n permute r, is an ordered arrangement in which r different objects are chosen out of n different objects and repetition is not allowed. So there's certain parameters that we need for a permutation. The first one is order arrangement matters. The second one is repetition is not allowed. So technically, through the examples that we already went over, we can utilize counting problems using permutations because there was a few examples that specifically repetition was not allowed to be utilized in. So let's look at the formula. N permute r equals n factorial, n minus r factorial. And what we have here on the left-hand side, what we have here is kind of the parameters that need to be met to utilize permutations. So the first one is the n objects are distinct. What that means is that you could tell them apart from one another. There's various labeling, various arrangements within that. Different coding can be utilized on it. 2 would be repetition of objects is not allowed. And then 3, order of arrangement matters. Order of arrangement matters. So what the n represents, and let's see if I can write this small enough here. So what n represents here is number of objects. And then what the p represents is permutation or permute. And your r is specific. Let's make that smaller. Specific arrangement. Arrangement number or specific number of arrangements, however you want to label it. And let's do an example of permutation. And through this example, I'll make connections to what we already did above in other examples. So it says here, in how many ways can people in a 1,000-person marathon finish first, second, and third? Okay, again, order matters here in this specific example because they're giving me placements. They're telling me that first, second, and third. There's an arrangement there. When you're running a race, I guess technically, right, in a weird example, there could be somebody that literally crosses the finish line at the exact same time as someone else, then you'd have a tiebreaker. But we're not worried about that. What we're worried about is somebody's going to finish, then somebody totally different is going to finish second, and then a totally different person is going to finish third. Well, what we'd have is, what is our number of objects? What is our n here? Well, how many people, right? People would be the object. Well, how many people are there? There's 1,000 people marathon. So our n is 1,000. And then remember, our r, what does our r represent? Our r represents specific number of arrangements. Well, how many arrangements are there? There's only 3, right? There's only first, second, and third place. There's only 3 arrangements. So how can we put that in, or what does it look like using our formula here? We'd have 1,000 permute 3, and in the formula, you'd have 1,000 factorial all over 1,000 minus 3 factorial. If you were to simplify that even further, you would have 1,000 factorial over 1,000 minus 3 is 997 factorial. I'm going to zoom out a bit, and I'm going to move this piece to the left, and there's a reason for that. Another way to write that part, right, the part right here, another way to write this, if we were to break that out a little bit, is this. This is the same thing as saying 1,000 times 999 times 998 times 997, so on and so forth, all the way till I get to 1. That's a long thing to write out. All over 997 factorial. But what I could do is instead of writing out the entire top part, if you just ended at 997 and put a factorial, because that means that it keeps going, then what you could do here is just cancel these out. And what you would be left with, is 1,000 times 999. Let me make that a little bit cleaner. 999 times 998. And now look, there's only 3 options. First place, second place, third place. And if you did that in your calculator, what you would get would be 997,002,000. Now, I hope the connection's being seen to what we did in our prior examples up above with the shirts and the pants. What other examples did we have up above here? The 6 factorial here in regards to our errands. Those would be very similar to what we did here. Now there's an easier way of doing this in your calculator, and I'm going to show you. All we're going to enter in our calculator is 1,000 permute 3, and it's going to give us this 997,002,000 down here at the bottom. So what you want to do, make sure your calculator is cleared, is you're going to put in your 1,000. Okay, put in your 1,000, hit math, go to your probability again, and notice you have the NPR up there at the top. Okay, NPR for permutation. Click that. My calculator is a little bit different, so let's hope this works. And then you want to hit 3. Oh, it's not going to do it for me. Let's clear that. 1,000 math permute 3. And I wonder if this one's a little bit different. So using a calculator, you would just hit 1,000 permute, hit the number 3, and then hit enter. Let me see if I can figure this one out, though. Looks like I'm going to have to put this first, 1,000, and then permute 3. And there you go. You get the solution that we just had. Again, this graphing calculator I have on my screen might be a little bit different, and I could tell already by the way it works, it's a little bit different. Usually you just need to hit 1,000, go to math. So 1,000, I'm going to do it on my own calculator off screen. 1,000, go to probability at the far right. It's going to be number 2. You're going to hit enter. So now your screen should say 1,000 NPR. Hit 3 for the number of arrangements. Hit enter, and you'll come to your solution. So my screen, again, on my iPad here, recording is a little bit different than what you'll have on your TI-84 Plus. And that is the conclusion of 4.5 Part 1. Thank you, everyone.